Good afternoon, everyone. My name is Andreea Dumitrașcu, and I'm delighted to welcome all of you to the 6th edition of Connect University Summer School. Established in 2015, Connect University is the knowledge-sharing flagship initiative of the European Commission's Directorate General on Communication Networks, Content and Technologies, in short DigiConnect, that aims to inform the public about the latest digital trends. Cutting-edge technologies placed high on the political agenda are presented with this occasion with the scope to foster inspiration, identify opportunities and threats, while enabling synergies between various EU institutions, industry, academia, and also international organizations. The Connect University project, in short, is a trademark for debate and policy advice, raising awareness about the ongoing digital revolution and preparing the society for the future changes. For today's session on high-performance computing and digital twins for climate action, we invite you all to join us via Slido using the code HPC. I repeat, the code for Slido is HPC. You can comment and ask us questions, and we will allocate them accordingly to our distinguished speakers. Also, please use the hashtag ConnectUniversity when sharing insights on the event on social media. Without further ado, I am pleased to welcome Ms. Grażyna Piewicz, Head of Unit, Open Science and Digital Modeling, DigiConnect, European Commission.
Yes, hello. Thank you very much. Good afternoon, everybody. It is my pleasure today to introduce this session. So I will make a rather brief presentation about an initiative that is part of the European Green Deal that is called Destination Earth. I will then hand over to our distinguished speakers who will follow up with very interesting presentations relating to that initiative. So if you could please start the presentation. Waiting for the presentation to start. Of course, yes, there it is. Very good. So just as a matter of a little bit of introduction, when we speak about climate action in the EU, I think everybody immediately thinks about the European Green Deal, which is the latest strategy of the European Union to respond to the challenges that climate change is bringing to us. The European Green Deal is, as I mentioned, a strategy which aims to make Europe the first climate neutral continent by the year 2050. And this will be achieved through the twin green and digital transitions. However, setting goals is really not enough. The EU needs bold and ambitious initiatives to make them a reality. And Destination Earth, which I mentioned at the beginning, is at the very heart of this strategy. Before I take control, maybe next slide, or I take control immediately. Sorry, I forgot to do that. There it is. Voila. See if I can control the slides now. There it is. So on this very, let's say, dense slide that you see here, I will give you several, let's say, details about what Destination Earth is. It is, in fact, one of the European Commission's flagship initiatives addressing the twin green and digital challenge, which I mentioned just a short while ago. This key initiative was announced in several initiatives or communications from the Commission, notably since December 2019, the one on the announcing the European Green Deal, then followed in February 2020 a communication announcing the European Strategy for Data, and finally the communication on shaping Europe's digital future. So this initiative is really present in all the major initiatives that the European Commission has announced as relating to the climate action. Now, what will Destination Earth, the Destination Earth initiative, do? In fact, it will develop a very accurate replica of the Earth system, otherwise a digital twin of the Earth, with unprecedented amounts of detail. This combination of unprecedented prediction and simulation capacities of this initiative, linked to ever more accurate and verifiable scenarios of potential effects on various socioeconomic sectors, will provide us with a true leap forward. How will it do that? In fact, the digital twin of the Earth that we are aiming to build with this initiative will allow us to monitor and simulate natural and human activity, and to develop and test scenarios to support evidence-based policy making at EU, national or local level, and their implementation. It will greatly enhance our ability to anticipate environmental disasters and also their resultant socioeconomic crisis. So technically, what is Destination Earth? In fact, Destination Earth has three main components. It will consist of the so-called core platform, thematic digital twins, and services that it will offer. So the first component, the user-friendly, secure, cloud-based digital modeling and simulation platform, will be the heart of Destination Earth. The platform will use advanced high-performance computing, and this is part of or an element where we link to this session. It will use advanced high-performance computing capacities for its modeling and simulation needs, but it will also use artificial intelligence and data analytics to deliver its services. With all this, the core platform will allow users to customize it, to integrate their own data into the platform, and develop their own applications on it. The platform will also federate and provide access to many relevant data sources, data lakes from our partners, and I will mention our partners a little bit later on. Those data lakes contain such data as atmospheric and climate change data, or the collection of data sets from successive Earth observation missions. It will also include data from European agencies, such as the European Environmental Agency, and this data will be, for example, greenhouse data, data on greenhouse gas emissions, data on air pollution, on renewable energy, on energy efficiency, soil moisture deficit data, etc., etc. There's really a plethora of data that will be included through these sources. Furthermore, there will be data from, for example, the European Marine Observation and Data Network, so all sorts of marine data. There will be seismic data, what have you, really a lot of geospatial, different types of geospatial data. But also, ultimately, data coming from the Internet of Things devices and users' own data. And the final component of Destination Earth, I should say last but not least, by far, are the digital twins, thematic digital twins, or thematic replicas of complex, interconnected natural and socioeconomic systems. They will be integrated into the platform under a thematic affiliation, such as extreme natural disasters, climate change adaptation, oceans, biodiversity, etc., etc. They will not only give users passive access to this high-quality information, services, models, scenarios, forecasts, and visualizations, but also enable users to actively interact with the system. The funding, just very shortly, for Destination Earth is mainly provided under the so-called Digital Europe program, which is a new funding program of the European Commission under the new multi-annual financial framework, so the overall budget of the EU. But Destination Earth will also benefit from funding available under Horizon Europe for research, supporting research activities. Voila. Why is Destination Earth important for the society and environment? Well, first of all, Destination Earth is about evidence-based Green Deal policy development and implementation at all levels. In fact, Destination Earth will develop user-centric knowledge to support the objectives of the Green Deal, as I have said. What it means simply is that decision makers will be able to act proactively on the likely development of environmental stress factors and their final impact on people and the environment. But also, they will be able to evaluate the impact of their proposed legislative measures and the effectiveness of their implementation. Those policy services at those very different levels and the general public will be able to understand, for example, impacts of future climate change on land use, on security of food supplies and water resources. Energy providers will, for example, be able to plan for long-term availability of weather-dependent renewable energy. And, for example, the civil protection sector will be able to test the effectiveness of their disaster risk management strategies. But Destination Earth is also about easily accessing data and benchmarking models. And what I mean here is that users from the public and the business sectors will be able to access, via the cloud, the Destination Earth models, algorithms, applications, and vast amounts of natural and socioeconomic data, and exploit them for testing their own models, for example. And last but not least, Destination Earth is about providing user-specific and actionable predictions on pictures of the future. So Destination Earth will bring innovation in the interaction with expert systems by generating actionable knowledge based on transparent models and data that will be tailored according to the specific interests of expertise of users. So the whole system will not be only for use by really expert users, those select few, but will be available for use to any of us. Sorry. What distinguishes Destination Earth from existing services or initiatives? Some of you who know Copernicus, the Copernicus program of the EU, may think that there is little difference, in fact, but there are significant differences. I will focus here on three key innovative features of Destination Earth that distinguish it from everything that exists today. First of all, Destination Earth will use the various diverse data sources that I have mentioned, including socioeconomic data, and fuse that data with simulation models. This is really an innovative new feature. Another key innovative feature of Destination Earth will be that it will provide an interactive simulation environment. It will provide users with services based on what-if scenarios, with the use of the platform's modeling, simulation, and prediction capabilities. But also, and most importantly, it will allow users to generate and test their own what-if scenarios. In fact, Destination Earth is about building, creating, and testing scenarios with the perspective of usage by non-experts, as I have mentioned. And on this basis, it is really meant as a true evidence-based policy support tool. Finally, Destination Earth will be distinguished by advances in mapping uncertainties, what we call uncertainties of the models, and communicating the resulting quality levels to support the decision-making process. This future ability of Destination Earth services, from both the digital twins and the platform, to communicate that uncertainty in a way that reveals the quality of the underlying science, will make Destination Earth a tool to ensure quality development and implementation of EU or national environmental and climate policies. So just a few final pieces of information on how the European Commission intends to, in fact, deliver this very ambitious project. The project is led by DG Connect. I have mentioned the funding under the Digital Europe program and Horizon Europe. We, as in the European Commission, is in fact now partnering with the European Space Agency, the European Centre for Medium Range Weather Forecasting, and the EUMETSAT, the European Organization for the Management of Meteorological Satellites. Those three organizations will be our partner organizations who will in fact implement Destination Earth, the Destination Earth initiative via the so-called contribution agreements with the European Commission. But the implementation of the initiative will involve a very significant participation of the European industry. And this will be ensured by way of procurement of specific solutions that our partner organizations will do on behalf of the European Commission. So when will all this happen? We are in fact gearing up to kickstarting operations or implementation activities rather soon, hopefully around the month of September, with the first implementation phase ending by 2023. But the entire digital twin of the Earth, the full digital twin of the Earth, consisting of all the different thematic digital twins that it will consist of, will most likely be delivered by the end of the decade. Just because it is a huge endeavor, very, very ambitious, very difficult to realize, and thus very, very lengthy. So this is all from me as introductory remarks. I will now pass the floor to the next speaker, Mr. Anders Jensen, who is currently serving as the Executive Director of the European High Performance Computing Joint Undertaking. Mr. Jensen has a lifelong interest in supercomputers, dating from his time in university. His professional career started with 10 years of engineering work. After that decade working with engineering and product development, Mr. Jensen joined a company called Cargolux Airlines International, where he was director of IT. After serving in Cargolux, Mr. Jensen joined the NATO, the North Atlantic Treaty Organization, where he was responsible for all implementation and IT services, as well as one of the largest classified networks in Europe. And now, since 2020, Anders was appointed as Executive Director for the European HPC joint undertaking. And that joint undertaking is a joint initiative between the EU, the European member states and private partners to develop a world-class supercomputing ecosystem in Europe with a proposed budget, well, actually now a budget of about 8 billion euros. So thank you very much from me, and I look forward to all the exciting presentations from the very distinguished and highly knowledgeable speakers in this area. Anders, over to you. Thank you.
Thank you very much for your kind introduction, and thank you for the invitation to come here to speak. Where do we fit in the joint? I'll take you through who we are, the joint undertaking, but also where what we've been up to. Where we fit into this is, of course, that we expect to provide quite a bit of the horsepower that Destination Earth will need in order to work, and we expect that Destination Earth will be one of the significant applications on the infrastructure that we're currently building up. I've been asked to provide a bit of an update. For those of, I'm sure most of you are aware, but for those of you that are not aware, the European High Performance Computing Joint Undertaking is very much a brainchild of DG Connect, and therefore it is also it's very nice to be invited here to speak at the Connect University. and very appropriate. The joint undertaking was created in 2018 by a declaration known as the Rome Declaration. But most importantly, we became autonomous in September of 2020. So we are a very new and young organization that has been spending its last 9 months trying to stand on its own 2 feet. We are headquartered here. I say here, that's because I'm sitting here in Luxembourg. We're headquartered in Luxembourg. We have beautiful offices provided by the Luxembourg government. And as of this morning, I called the lucky person that's going to be staff number 15. So that gives you a bit of an insight into just how small an organization we are at this point in time. We are looking to grow. So as you watch this presentation, if anyone's sitting out there thinking this could be a cool place to work, I can't emphasize enough how you should then look at our website, because we will be hiring quite significantly in the fall. The joint undertaking, our raison d'etre is twofold. On one hand, we will be deploying a top-of-the-range supercomputing infrastructure across Europe to support the European researchers and also to provide some access to industry. The idea here really is to get supercomputing infrastructure, to make supercomputing infrastructure easily available. In parallel to that, or alongside of that, we also support a very ambitious research and innovation agenda to develop the HPC ecosystem in Europe, and as well as the supply chain. So this is very much about helping industry researching in the various hardware, software applications, and so on. But also, very importantly, programming the HPC computers is not just a natural continuation of programming normal computers. So there's quite a bit of training that is required, and that's also within the area of responsibility of the joint undertaking. We have 33 participating states. So so we have some countries outside of the European Union, including Switzerland, Norway, Turkey, and we have private members. As we are joint undertaking, we have 2 private associations with us, Big Data Value Association and ETP for HPC, which provides us the industry input into the joint undertaking. And sits on 2 advisory panels. We have a research and innovation advisory group, and we have an infrastructure advisory group, where the joint undertaking gets advice from its industrial partners about what we should be focusing on. Now, the infrastructure side of the house, you can say, of the joint undertaking is what's getting a lot of attention at the moment, because I don't think many people are able to say that they signed the procurement for 7 supercomputers within the space of 3 months. That is what kept us busy leading up to within 2020, and we're now busy taking delivery of these machines across Europe. Basically, what we've procured so far are 2 Preexascales. There's another one coming, but so far we have 2 Preexascale machines on contract. What we mean by Preexascale is that these are computers that are just the notch before what is known as exascale computers. Now, that means I have to explain what exascale computers is. Well, exascale are computers that are able to reach or compute 1 billion instructions, floating point instructions per second. So, of course, this is enormous horsepower. Alongside of those, we have 5 smaller machines in the petascale class. So these are thousands of billions instructions per second, and these machines, as they get installed, will be will be the infrastructure for the moment. I'll get on to the future. We have a third machine that is expected to be built up. You can see it still in Spain. We're still, but that one is not under order yet. So if we look at this so far, we have spent, the Union has spent 163 million euros on this. The total contract values were at 360. If we look at the timelines, which is of course what's interesting for projects like Destination Earth, but there are many others waiting for all of this capacity to become available. I was very pleased to see the first machine went live, and we announced that in March, which was the Vega machine. Following that, we just inaugurated the Melixena machine, which is located here in Luxembourg, not far from where I'm actually located. And we're still in the very final part of the acceptance of that. It should be operational within days. Then we have, that will be followed quickly by a machine in the Czech Republic, Carolina, as well as in Bulgaria, the Discovery machine. And then we'll have a bit of a wait until we get to about the latter part of this year, where we will see Decalion, the last of the petascale machines, go live. And then we'll also start seeing the bigger machines. So Lumi in Finland, as you can see there, it has a contracted performance of 375 petaflops. We will see the first partition of that in November, and then the full capability around March timeframe. And equally in Italy, the Leonardo machine will also be split over 2 deliveries. Just as we are, as there's also a focus on green, I think it is very important to point out that in all of these procurements, and also going forward, the JU takes particular care to also look at the energy footprint. It is high performance computing is extremely expensive from an energy point of view. First of all, we need the energy to go into the machines in order to do the calculations, but we also, that unfortunately creates a lot of heat. So we also need to consume energy, or to consume energy in order to cool the machines, get the energy away. So in all the procurements that we've done, there's been special focus on the energy profile, not only of the machines that we're putting in, but also of the facilities that will be hosting it. So there's some quite interesting solutions. For instance, the big machine in Finland will get its power from a hydro facility, for instance. And here in Luxembourg, we have equally some very interesting power arrangements with some cogeneration that's not only generating the power for the machine, but also actually helping with the cooling, taking away the excess heat. So what all of these machines, as they come online, how do you get access to them if someone's sitting out there feeling like running some code on them? Well, for that, I would encourage you to visit our website. The governing board has agreed an access policy that will be testing now with the first machines coming online. There are a number of types of access that you'll be able to sign up to as we go out and make the machines available. As I said, we're testing it, we're test driving it. So far the access policy will be valid until the end of the year, and then the JU is expected to put forward an amended version to the governing board based on the experience that we will have from the initial applications. It is important for me to point out that for those of you that do not know, there is an initiative, there has been an initiative for many years in Europe known as PRAISE, that have done coordination of HPC facilities across Europe. We are working closely with PRAISE piggybacking on some of their experience in and around this access system, and also on other things, so that there's continuity and that the scientists around Europe don't all of a sudden see the whole way they have to interact regarding HPC changing. So that was the infrastructure side. Now, there's an equally important side, which is our research and innovation. And basically there we have a number of research and innovation activities already ongoing. This includes pilots, so we have a couple of pilots in and around future European supercomputers, so the technology going into the future supercomputers. We're also looking at, we have a pilot regarding quantum simulation. I'll get back to quantum a bit, but it's something that the JU will be doing quite a bit more under the new regulation. Then we have an initiative, again, back to green. We have a significant initiative that's been going on for a while to develop a European low-power microprocessor technology that can be the heart of a future exascale computer, and this is known as EPI. And those of you within DG Connect, I'm sure you're aware of this initiative. It's been going on way before the joint undertaking, but it has its natural home now in the joint undertaking. And phase 2 that's coming up, we will be taking that on. Then we will be on the software and application side. We will be looking at funding actions that helps applications transform so that they can better use all the new technology that's coming in. The difference between some of the smaller machines and the bigger machines is very much on the type of technology that's in the machines, and the technology that's in the big machines will require rewriting of software, and therefore we're supporting actions in which some of these applications gets modified so that they can take full advantage of the future infrastructure. On the skills and training side, we have our HPC competence centers, which will be supporting the European community. We are stimulating work with SMEs, and we're progressing on training and education within HPC. One thing to note there is that we currently have a call out for a Master of Science program in HPC. So I touched upon new regulation. Basically, the regulation that we're working under right now takes us up to this year, but we now need we need a new regulation so we can continue to operate. This new regulation has been under discussion for a while, and it's very close to being there, and essentially will allow us to do more of the same as well as a lot more. And by what I mean by more of the same is that we will continue to invest in infrastructure, even bigger machines. The new regulation foresees 2 exascale machines, so these are even bigger than the big ones we're currently installing, as well as we will get into quantum. So we'll be investing in quantum infrastructure to make that also available to the European user community. And on top of that, we will be investing in what's referred to as hyperconnecting the supercomputing. So this is really about interconnecting and the computing resources across Europe so that the access to them will be much more seamless, and you can have data in one site and processing power on another site. There's the whole authentication. There are a lot of challenges. To a large extent, Destination Earth is actually an interesting is an interesting project to look at, because they will probably be piloting some ideas which we hope to be able to use. And then just summing up on where we're going under the new regulation. You see the funding there, which is the funding coming from the union. Then everything will be matched by member states. The way the funding works in the JU is usually a 50-50. So the union, the JU, will pay 50%, and the participating states will pay the other 50%, which essentially means that from a budget point of view of what we're trying to do, you can multiply these numbers more or less by 2. I do say more or less because in some areas we do fund 100%. As you see, more infrastructure, we're going to have more technology, but most importantly, we're going to be focusing a lot on the applications, because all of this infrastructure is worth nothing if there's no applications to run and use it properly. So with that, I conclude my little presentation of the JU. As I said, with the new regulation, we will be allowed to hire beyond the 15 people that we currently have. We will be looking to grow significantly. So if anyone's sitting out there thinking this could be a lot of fun to be part of, then please follow our website, and in general, follow our website for information. You will also, if anyone's interested in the more technical specs of all of the machines, they are also available up on our website, so you can get more information about just exactly what hardware is in there. And then, of course, finally, you're also welcome to reach out. So with that, I will stop my presentation.
Thank you so much for the very interesting presentation. Indeed, the participants are also thanking for giving this insights on the EuroHPC. Meanwhile, we have received some questions for you. So I will ask you the most voted question, referring to where are the systems, machines manufactured?
So a bit all over the place, to be very honest. Maybe that's something I should have touched on in the application. One of the things we were going for was architectural diversity. There was no, it would be pointless to buy 7 exactly identical machines and put them up. What we really want is for the European users to be able to use various types of machines and with various architectures. So we have a number of machines that are being supplied by Atos. We have a Japanese machine, which I personally think is cool because it is a baby version of the current #1 machine in the world, Fugaku. So that's Japanese built. That's going to come into Portugal. Then we have in Finland, we have a Cray from. Today they're owned by HP, American system. Yeah, I think that takes us around the suppliers.
Thank you so much for this. A similar question from a colleague in Connect. I was wondering if EU has control of the basic technologies like memory, CPU, GPU, etc. needed in order to build destination Earth and the described HPC.
So I think the answer is yes and no. There are technologies in which Europe is leading, especially in the cooling systems within the HPC and some of the software within the HPC. There are other areas where we would like to strengthen our industries and our knowledge. And the European Processor Initiative is an excellent example of a place where it's been identified that we need to do more, and the JU's mission is to foster that ecosystem and promote the better, well, what should we say, that we get better knowledge within certain areas within Europe.
Thank you so much for replying to the questions and also for the very interesting presentation. I'm afraid that in terms of time we would need to move on to the next presenter. but we will get some time for Q&A also after all the presentations. So without further ado, I'm pleased to invite our next speaker, Mr. Peter Bauer, Deputy Director of the Research Department at European Centre for Medium Range Weather Forecasts, to tell us more about Earth system digital twins taking supercomputing to the next level.
Thank you very much for the introduction. I hope you can hear me and see my slides. Indeed, thanks. Indeed, I'm trying to make the link between the two previous presentations. So I'm trying to dig a bit deeper into what Grazina has shown related to Destination Earth and the digital twins that will compose one of the parts of Destination Earth, and why this is very computing and data intensive and therefore needs to rely on EuroHPC. The timing of Destination Earth with the progress of new technologies, as Anders has just presented them, is ideal actually for making taking the best benefit from these investments. I'll start with something I tend to show at the beginning to make people realize how important the issues are that we're trying to address with Destination Earth. And this figure is published regularly and updated by the World Economic Forum every year. And it shows the distribution in terms of likelihood and impact of the top risks as perceived by a very large group of stakeholders, both public and private. And the worst place to be is actually in the top right, where both likelihood, so the likelihood that something happens, and the impact that it's going to have if it happens are equally large. And if you look at that graph, you see that if you can't read it, it says climate action failure encircled in red, biodiversity loss, human environmental damage, and extreme weather. And all those topics are in the focus of Destination Earth. So Destination Earth obviously is aware of this and is trying to focus on those risks that are increasingly likely and increasingly impactful. One other point I want to make before I go more into computing is if you Google big data, because big computing, should not be disentangled from big data, because in the end, nobody really cares about the computing except the computing people. In the end, it's all about data. So whatever we do in simulations or observations is data creation through computing or observation instruments and these kind of things, or the IoT. But in the end, what we're trying to do is we're trying to turn data into information and information into insight. And I would even go further. We're actually trying to turn insight into decisions. And that's something that Grazina has been very vocal about in her presentation. And so if you look at examples of this kind, where you're trying to turn data into information, that into insights, and that into decisions, you could look at value chains that are related to weather or climate, like this here, where you have an atmospheric situation bottom left, like a high pressure system sitting over Europe that might be occurring more frequently in the course of climate change in summers in Europe, for example. And that might create more frequently the coincidence of heat waves and droughts. And those heat waves and droughts have impacts in different ways. They stress the vegetation. There might be more forest fires. Forest fires create pollution, and that affects health, or vegetation stress can lead to crop failure that has an impact on prices and can create instability. So if we look at climate change and extreme weather or all the risks and impacts I mentioned earlier, we have to always think through these value chains. So a digital twin that stops at by creating forecasts of temperature and precipitation is only worth half the bill. We really need to make sure that we connect this to what actually matters to society along all these value chains. And that's also at the heart of Destination Earth. The advantage that we have at the present time is that Europe can build on a lot of world-leading capabilities in many different areas. And one is the world-leading science capabilities. And I'm sure Pascal Braconneau, who's going to give the next presentation, is going to tell you something about progress in climate science and where we are in terms of reliability of climate predictions. And just recently, the Royal Society, spawned by the organization of the next climate conference, the COP26 in the UK, in Glasgow, has published a position paper outlining 12 important technology and climate research priorities for delivering net zero carbon emissions by 2050, which is at the heart of the European Green Deal. And if you look through these papers, these 12 papers, you find exactly the terms that we have picked up with Destination Earth. For example, in terms of climate modeling, that's the box on the top right, where it says high resolution climate resolution to harness the power of exascale computing. You know, exascale was explained by Anders. Or below, digital technology, access to huge amounts of data, computing science, and digital twins. And again, this is reflected in Destination Earth. So very good timing and very ambitious. But it's not only the world-leading science capabilities that we have in Europe, we also have existing prediction systems, either in terms of weather prediction, like the place where I work. ECNWF is an intergovernmental European organization that sits in the UK. It has its dedicated computing system, and that is, you know, it's not pre-exascale, but it's pre-exascale, maybe. So we have a dedicated system to run our very complex weather digital twins, if you wish. And we create huge amounts of data sets, as you can see on the top left of this slide here, that is disseminated to millions of users. But you also have the Copernicus services that Grażyna has mentioned, and you see the time series there of one of two services. One is the one on climate change, the other is on atmospheric monitoring that also covers pollution, for example. And you see those were established many years ago, but have at least a superlinear growth in users of many, many thousands per day. And we in Europe actually have the world-leading prediction capabilities in both weather and to a certain extent in climate as well. So we can build on both science and prediction capabilities already with Destination Earth. So we hit the ground running, if you wish. But we also have world-leading technology capabilities. Anders just gave a very good overview about the huge European investment in HPC. He mentioned different types of technologies. He mentioned the interconnectivity of these systems. So it's away from this concept of HPC centric operation of HPC capabilities, but rather towards a network, a federation of such systems where you have access to different types of technologies, obviously with a very good interconnection that he called, I think, hyperconnection. But we also have very large software development programs. He mentioned the need to adapt applications to different types of technologies, and that's not just processes, that's memories, that's data-intensive workflows and all that. And Europe has a world-leading history, actually, in developing these capabilities, also funded by the European Commission. For our extremes case here, we have already some examples of digital twins leading to Destination Earth. We have a center of excellence called EasyWays that is also funded by the European Commission that supports these developments. And we're testing right now some of our applications already on the world's largest computers all over the world. And of course, with Destination Earth, we want to scale this up and bring this to EuroHPC. Just a quick back of the envelope cost estimation, because there are questions about, is it actually worth investing in HPC in order to support some of these applications? And there's lots of information about such calculations available on the internet. For example, us as a European organization or intergovernmental organization, we have to justify to our member states the huge investments we make in our HPC system, and whether doubling the budget for HPC, for example, is worth making. But if you look at the numbers that are available out there for both weather, climate, extremes prediction, you end up with a return of the investment in factors of 10 to 50 to more, depending on the applications you look at. So for every euro you spend in HPC, you get 10 euros, 50 euros or more back in terms of the value that generates. So it's money very well spent. But as previous speakers have mentioned, it's not trivial to put these applications onto the new technologies and exploit their full potential. Number one, we expect the digital twins to pose problems that are of the order of a factor of 100 larger than what we currently do in terms of computing and data handling. So this requires a significant scale up. And then also these new technologies and the diversity of these new technologies are not easy to squeeze performance out from when we look at our applications right now. We might be running on petascale or exascale computers, but we're nowhere near actually using the full computing power or data handling power of these systems. And the bottom right is a figure that will take some time to explain, but what it basically tries to summarize is the different axes. So these are the radial axes here in this graph of where we want to invest in and which methodologies we need to actually achieve that expansion in all directions at the same time to create the best value for money. And that means going back to the drawing board for our numerical methods, the way we design codes, which algorithms we pick, how we invest in machine learning across our workflows. We need very specific programming models to deal with GPUs, for example, or even more advanced and more specialized technologies in the future. And in the end, it takes quite a good diversity and good mix of processing and memory architectures to serve our very specific workflows. So a lot of the investments is not in hardware, it's investment in software, in people, to make sure that we can exploit the potential of that hardware. In terms of data, the computing is obviously, in terms of data, we have a similar challenge. And the figure that you see here is a typical workflow that we use where you receive observational data on the left-hand side. You bring this together with simulations to create digital twins in the middle, which is very HPC-centric. And then you produce products and disseminate to users on the right-hand side and put that in the cloud, for example, and make this accessible through the core service platform of Destination Earth, for example. And machine learning in particular has a lot of potential along the entire workflow that is shown here, not only for better understanding how to use observations, for example, from yet unknown and unexplored sources like the IoT, but also for data compression, for example, for conserving the information at the same time, but doing clever information extraction at the back end to reduce petabytes of data to kilobytes of information to feed decision support. So there's lots of challenges there in all these boxes in that workflow, and machine learning can help us. But just the variety of topics I've mentioned show you the breadth and width of software development challenges we have and science challenges that get along with that. So we need to invest in all these areas at the same time. On the right-hand side, I mentioned the good timing of EuroHPC, promising to take over some of the resources that we require. And on the left-hand side, what we want to achieve is that we create a fairly convenient access platform that is hiding away a lot of the complexity that sits under the hood that creates all this data and uses all this computing, so that users of very different and diverse backgrounds can actually play with the information and derive the information they need. So at the very end, digital twins are central to the Destination Earth action, and EuroHPC is a necessary condition to realize this. Destination Earth and the digital twin addresses maybe the most critical challenge of our time. Fortunately, we have decade-long investments in Europe in excellent science, world-leading prediction capabilities and digital technology, not the least supported by the European Commission through very well-established programs. And we expect Destination Earth to create yet unprecedented impacts on society's science and technology at the same time. And we promise also a very decent return of investment in terms of HPC, as I mentioned, because Destination Earth will be maybe the poster child of early EuroHPC allocations. Thank you very much for your attention. I will stop my share now and take questions.
Many thanks for the very interesting presentation. Moving now to the questions from Slido. There is a participant asking more precisely what is the role of machine learning and HPC in climate change, and how do the data-intensive problems change the requirements on programming support and architecture?
Yes, I guess I've covered some of this in my presentation. So let's start with the machine learning. So if you look at observations come with very different quality. We need to understand the quality patterns and the information these observations provide and how to combine them with the simulations. And here machine learning can help us do that and make that combination between observations and simulations and characterizing errors in both a lot easier. A very important, and maybe to me the most important benefit of machine learning in that context is to extract information once the primary data of digital twin has been created. As I mentioned, we will be creating petabytes of data, maybe per day actually, through the digital twins. And to then extract information for an energy company or a climate scientist or a civil protection agency is very different problems, with very different requirements. And to do that requires machine learning and the understanding of what these specific requirements are and how to extract the patterns that are relevant for such communities specifically. Programming support, yes, I mentioned also the diversity of architectures and technologies related to processes, memories, workflows that are very data intensive. Not all of the architectures that are presently available or becoming increasingly available are very well established, come with very established standards in terms of programming. And a lot of our domain-specific applications like climate models or weather prediction models or data simulation systems rely on programming models that are fairly outdated. So we have to make quite radical changes. And this is what I tried to show in my graph with this hexagon. Which requires the recreation of codes, rethinking about algorithms and methodologies, and probably recreating some of the programming support ourselves actually, and not waiting for standards.
Many thanks for your reply. We will now move to the next presenter, as we are aware of the timing. Hence, I would like to invite Ms. Pascale Braconneau, climate scientist in the Climate and Environmental Sciences at the Institute Pierre-Simon Laplace, to tell us more about multi-phased questions and challenges for climate projections.
Okay, thank you. Can you hear me?
Yes, I confirm that we can hear you.
So I will have an academic point of view in this presentation, so that to try to show you how we think this question of climate projection and anticipating of the future with very different time scales. So I'm putting this slide to start with just to remind what's going on. Earth has known a lot of climate change in the past, and it's the evolution of temperature here as a function of time. It's a logarithm axis on the x-axis. And then we have the present day and the future coming in. And the problem we have now is that human activity is a key player in the climate change, which was not the case before, because this was mostly natural variability with lots of variations. And the magnitude, we all know that, and you see it on this figure where you have climate projections. We are in a if hypothesis testing, where we want to know what if we are doing something with our emission, what's going on with climate. And of course, it's easy on figure to show you only a global temperature because it's a global change, but we have also more information for that. One of the difficulties we have when we're thinking about climate change is that there's lots of different factors interfering. And it's also the fact that in practice, our civilizations developed during the Holocene, the last 10,000 years, where finally at global scale, not local, but global scale, the climate was rather stable. And suddenly we are doing something that is larger than a deglaciation, for example, but in a century or very short time. So we even do not know if sometimes what we are developing for present day is still valid when we project to 50 or 100 years, and what are the risks in front of us. So that's part of the question we have. So I have a few slides in practice. I will complement with my background of 70, I would say, those of Peter. I did just to remind that, yes, we are using this big model. We call that Earth system model, and we tell a little bit more about them. And in practice, when we think about it, it's a chain of models from theory, numerics, informatics, and so on. And it's also a computer, the way you run your simulation, the monitoring of them, the access to data, data storage, and analysis of the results. And when you're someone like me with time, it's rare when you can fit everything at the same time together so that you can go one step further in your understanding and the way you run your simulation and you can understand the results. So each of these pieces is a research sector per se, and we absolutely need in all the development, and I hope in digital connect to have all people working together to make sure that all the solutions can work and are adapted to the different questions we're asking. So models we're using are a long history now. That in the 90s, it was only atmosphere models, and we had ocean atmosphere coupling and also coupling with land surface. And then now we have more complexity with biochemical cycle and so on. But the pathway, depending on the different groups, is still heterogeneous, and there is no model available today with everything in. So why is it so complex, and why are we not going that fast? The part of it is that because the question is very difficult, and we have lots of time scales to accommodate. For the fast time scale, the atmosphere, the first layer of the oceans. But then when we think about climate change, we have to look at the implications between these rapid feedbacks on a few days and months and even years, and what's going on with slower feedbacks that involves the mid-ocean or deep ocean, or involves a change in the land surface, for example, for a change in ecosystem that would feedback in the climate. And these slow feedbacks also act to shape present-day climate. So we have all these dynamics to take into account. So the models in practice we are using are, depending on the groups, that we are trying to have flexible models, even though this has to be revisited every day, so somehow, where you have atmosphere, ocean, land surface, sea ice, and everything coupled together. And more, you have the physical part of it, we call ocean atmosphere model, that are coupled also with biochemical model in the ocean, vegetation with dynamical vegetation that can change with climate change, and also all the atmospheric chemistry, so that we can go one step further. For example, the model we are developing at IPSS, so is that each component can be used in standalone mode, and in particular the same code we're using, so there's a lot of things to do so that it's flexible or in the couple mode. And also what is more and more interesting for the linkages with society is that when we add these biochemical models into the system and they're becoming more and more complex, you are closer to what you need to go to impact studies, for example, linkages with fisheries or linkages with agriculture. Okay, so the big deal for all of us, we know, is the scaling interaction. So there are multi-scales. There are lots of progress everywhere in the atmosphere, the ocean, and so on. And Peter has shown a very nice example of that. There's clearly a need to be able to go across this scale more easily than what we are doing now. It's a big challenge in practice because it's not exactly the same system each time you're looking at when you move from one scale to the other, but they need to be absolutely compatible. So what the major advances now have been done either, I would say, in the very fine scale in the last years, also for paleoclimate, where we are able to run now for millennium scale and more the same model version than the one used for future climate. But what's going on if we have very high resolution model in general do not have the slow component active in the system, and the ones that have a slow component active are lower resolution. So there is really a need to figure out how we can go across these scales, across this model, and be able to browse in a consistent way all these time scales. Okay, so when we are doing also climate projections for the future at different time scales, you have also to deal with very different perspectives and connected needs. So that's clear that for people like me, I'm an academic, so I really need to understand the system and to make sure what we are producing makes sense in terms of physics, dynamics, and results. We have to characterize lots of different things, including the methodological changes on a small time scale, extreme, and possibilities for abrupt event and so on. And with these projections, we are testing lots of hypotheses on human activity and the way human activity is affecting climate. And this has an important role and is the basis somehow for information, to inform climate services, that we are more for decision makers in terms of mitigation and also adaptation. So lots of different things. So what's the first thing we are doing? When we think about anthropogenic perturbation in practice, we are thinking that the human activity is perturbing the energetics of the system. So that what we need to know is how big is this energy perturbations and what are the implications on the dynamics and everything. So we have to deal with natural forcings, solar, that is the heat engine of the system, like can be volcanisms also coming in from time to time, but also different types of human activity, emission of trace gases, aerosols in the atmosphere, and also land use and deforestation and so on. So this we have an idea, so we need to know what's the exact emission and everything we have to include in a simulation to do that, so that the model itself has summarized it as being able to think about the radiation perturbation in the system, both globally and at regional scale, and the regional is becoming more and more important in our thinking, so that we understand the direct effect on climate and all the feedbacks that shape the climate change response. So the way to do it is that you cannot work alone, again. So on one side, we have all the computing, and the other side, we have all the people running assessment models simplified from the climate part, where they can build on ideas about society and economics that can tell us what's going on in terms of emission, land use, and aerosol emission also in the atmosphere. And then the way we proceed now is that those people have decided to work with different worlds that have different challenges in terms of mitigation or in terms of adaptation. And you have different types of societies where you can have regulations for the emission, for sustainability, for example, or rapid growth or use of energy. I will not go into the details, but at the moment, we are thinking with 5 of these families. And for each family, there can be different trajectories in the emissions. And these different trajectories give you different radiative perturbation in 2100 here at the end. And of course, not all these trajectories are compatible between the different families. So when you're running the big model, the big Earth system model, it makes no sense somehow to run all these trajectories. So to have the exercise at global scale with all the modeling groups gather as part of what we call simulations, it was decided only to pick up some of these trajectories so that we sample both the different societies and trajectories in terms of emission, land use, and so on. And part of it also is a compromise, so that we want to test if we are able to stay below 2 degrees as part of the Paris Agreement, so that the scenario 1.9 and SSP 1, 2.6 there, or if there are other trajectories with lots of emissions. So we're not going to the detail, just to remind you what we're trying to do. But for a climate person like me, with this projection is not only to provide simulations to other people, but it's also to understand and also for others, you also need to understand what's going on. So we need to explore. So we need to explore the all forcing together, the individual forcing, the multiple question on warming, precipitation, and hydrology at global, regional, and local scales, and with different types of horizons. We need also to test if we understand the system, which means we need to have idealized experiment to test our knowledge and also test the model content. So for the same, I would say, trajectory test, in practice, we are a lot of ensemble, not only to sample variability, but also to sample the way the system behaves so that we have a good information and understanding. And of course, we think about what's going on at regional scale and the linkages with other sectors of activity. And this, we have to think about the scale interaction and downscaling, the fact that models are not perfect and need to be corrected, and that we can have online some specific indicators already computed, or be able to run additional simulations so that we have better linkages with impact studies. But still, this is not fast enough in the way we go between people. So all this question is the reason why finally an exercise like the symmetries exercise with all the projections, but not only, for all the simulation we need to understand is so big, because we are trying to make a mixture between providing something for projections so that people can use, but also all the understanding in lots of subjects and lots of them. So in this exercise, we have a limited core experiment that everybody is obliged to run so that we can share, see where we are between, what's the state of the art between all those simulations. We've also idealized simulations and also 23 endorsed MIPS in their comparison to cover all the different questions. Okay, and then of course you need to distribute the data. So the way it's done now is through the Earth System Grid Federation. So there's lots of investment everywhere around it so that it's flexible, accessible by lots of people. Of course, it's still very complex because the exercise itself is very complex and it's going on, it's improving every day. And in Europe, it's an easiness infrastructure project that helps to develop all this, and Peter had mentioned it, and also it contributes directly to Copernicus for climate services. So this is still evolving and it's lots of connection, but it's very important for us that everything is shared, and it's shared very rapidly to a wide community, and not only the scientific community. So for the exercise, as a flavor of it, new projections, you can find out what's the change in temperature and where are the regions that were more than others, the same for precipitation. Lots of questions about when you cross different warming levels, because it's important for impact studies and it's also important for assessments. New questions arriving because some of the new models, when you compare the blue dots here for the previous exercise to the orange one now, have a larger climate sensitivity so that there were more than before for a given change in greenhouse gas in the atmosphere. And then it might be a concern. We need to check that it's not a problem with models, but because this climate sensitivity is also used in lots of applications as a very simple way to consider climate. We have also more complex model now with a biochemical cycle and the introduction of a nitrogen cycle that tends to reduce the spread between the result of different models. You can see for the CEMIC 4, 5, and 6 here, the last one. And then you can also derive lots of indicators, for example, some that can be directly linked to health, like heat stress, that involve a combination of temperature and humidity, and not only the evolution, but the rate of change. And it's just an example here showing that in the equatorial belt, it will be twice as large as this is today when you see the range here by 2020, 2025 compared to present day. And also lots of questions on the ocean and difficulties we still have at all resolution with the ocean circulation and what we call the overturning circulation, but that has also an impact on the way the model can warm or the climate in Europe for sure. Okay, so lots of different aspects, and I just would like also to remember that sometimes it's very difficult to know what's really a good or a bad model, because it depends a lot on what you're trying to do, and also a lot what's your concern. If you want the best range, you can, or if you are targeting particular application. And then depending on what you do, what kind of the model content is important. Unfortunately, it's still a parameterized model, and we remain part of it for a long time. So these parameters also affect the simulations. You have internal variability, and internal variability can mask your signal or mask the interaction between your signal and this variability changing with time. We have also uncertainties in forcing. We are imposing to the model what's the right forcing or the combination of forcing. And also, even if everything is perfect, the way you include them in the model can depend from one group to the other and make also some differences in the simulation. So all this needs to be quantified, and uncertainty need to be quantified. So lots of different levels to evaluate the model for process, mean state, climate feedbacks, and also paleoclimate that can tell if we are able to do something that is as large as what we are going to have. So there's increasing methodologies, and the very important aspect with machine learning, objective metrics, and so on, with statistics. But the very important aspects now I see is that we need to have more process-oriented studies and analysis of typical events that make sense depending on who you are and what's your application. And then we need to be able to grab all this in the simulations very easily. Okay, so lots of way of development, and to be honest, we need all of them at the moment, because there's no single one that can make progress. Even though we know we are still problems with cloud, so resolution is key for that. But we also know that 20 years now we're speaking of this, but most model, the I sheet is still not there. There can be rapid changing the I sheet, and it has lots of implications for sea level rise, for example. So we need to accelerate and go faster to exascale, be able to do it, because it needs lots of people to be able to make these transitions, and also think about the data volume and increasing data volume. So for Europe, there has been also some paper about it as part of business, and the latest one you have access here, Okay, so we are also thinking a lot of how we can go faster and use this new methodology, uncertainty quantifications. What we call tuning the model is to adjust them, and so that each time we have a change, we go fast. And is it possible to do this only automatically, or do you still need expert judgment and specialists? The response at the moment, and there are experiences with that, for example, at LMD in IPSL, you can run very short simulations and a very long large number to have first ideas of what's going on with your clouds, the radiations, and also high precipitation. So that is it possible to have these different targets at the same time, and without degrading too much one aspect or the other. So we think that it will be a way to go faster, and go faster in exchanges between different communities if we can adjust. Going forward, Peter has already mentioned it, there are lots of interlinkages between mid-scale and environmental factors, and it's just an example here extracted from Alan et al. That try to put together all what you need from the hydrological cycle if you want to relate your heavy precipitations to floodings. And that's clear that we need to be able to include in those simulations more and more human activity. That means have the cities, their impact, also deforestation, land surface. And it's why also you need the longer term, because there are lots of things going on with soil, and the story of your soil is also something important in that case. So all these feedbacks means that you need flexibility and think about a system that lots of people can grab, but also never forget that it's a lot of science behind there, and lots of connection and understanding that is still in its infancy. So lots of, I would say, research development to do to go in that direction. Okay, so we have to think about our possibilities to store the information. I've just grabbed this example because I find it funny and I think it can be very useful. Is how you use these new classification methods based on artificial intelligence and analogy with what is going on for text, where you can grab words, very small pieces, and then you can look for motifs, that is color, fruit season, depending on what you're doing and you want to do. And you can try to use the same methodologies for the climate simulations or for the data, where you're grabbing some motifs of anticyclones and depression and lows, for example, knowing that these basic pieces in practice is the relative strength that is involved when you have variability events or extreme events, is compound events between these different variability for one region. And there might be a way that you're not able to store everything, but figure out how you keep only the key elements you need to be able to analyze more rapidly the simulation, or to provide more rapidly some very useful information to different people. Okay, so I stop here. Just to say that is still a lot to do, so it's very exciting to see that, and we know that what we have done is only possible because you have close collaborations between people in the science, I would say, knowledge of climate, and also informatics and the computing, because otherwise we cannot do what we are doing. The problem to solve is huge, and it's becoming even bigger every day, because we don't want only the blueprint of the response. We want to be able to go to regional and local scales and have interaction between the various factors. So we are there now on the left with what we're doing now. Even though we are already including anthropogenic factors in our climate model, we want to go to something where we have more connections, and even the pieces of this big model can be used as entries, direct entries, or directly used for impact studies, so that its impact is no more seen as an impact, but also the feedbacks and all the interactions in the system. There is a lot to do. People in practice are ready to do it, but the problem is that it's huge. You need lots of people to engage in that. You need to not only serve the user, but work with them. It depends on very different kind of users. It's multidisciplinary research, and we hope we have a chance to do all this. And it's part also of our climate research program, where the new plan is really going in that direction. Okay, so thank you.
Thank you so much for the interesting presentation. We have a few questions from the audience before moving to the next presenter. And someone is asking about the possible bias that the scientists can get when they run experiments on climate models, and also about the main limitations in climate modeling at the moment.
So the first question I didn't capture. So for the second one, that's clear that I've seen in the first graph that what we are doing in practice is we have to adapt it, develop lots of different factors with the model contents, the way you run, how you look at the results. And at each of these pieces, there is still a need to lots of thinking behind that to be able to do it. And my feeling is that it's clear that all the pieces have increased. And I really would like myself to be in the position where I can run really a physical experiment where you have the pieces and the complexity you need. And that's a very important question. Depending on what you're doing, you need different complexities. But then you can not increase your complexity, but decrease it, so that you stop one process compared to the other. We are still not in this position. And then it limits also the understanding of the way the climate behaves. So that's part of the limitations. The limitations also is really multidisciplinary in all directions, and you need to make sure people understand each other, because when you build such system, it's not only, oh, I put things together. You need to make sure that those things you put together are really consistent, and then you have the same level of complexity between them, and they are built so that they can interact. And there is a risk in practice if you pick things in all directions, that you build something that makes no sense, even though all the pieces are really an atmosphere and ocean and biochemistry and so on. So that's a long process for these assemblages. And I think part of the limitation, and for myself it's clear, is that it's so difficult to run those simulations and huge, that sometimes you just stop dreaming, because you really would like this to be effective and more easily, and that's really where we need to go. So that's huge what we are doing. We are doing everything at the same time, and all the components, all the Earth components, not only climate but also the biological cycle together, the input from society, what's going on, it's huge. So that's it's a long way.
That's for sure. And I also take the opportunity to answer to the few questions related to the recording and the presentations. So indeed, all these materials will be able for further review. The recording will be ready most probably as of next week. So we will do our best to post the product as soon as possible. And you will find it on our Connect University webpage in the video space, as well as on YouTube or Digital EU channel in the Connect University playlist. So all the materials will be available to you for further review. So once again, many thanks for the presentation. And now we will move to our next speaker. And I would like to invite Ms. Alice Steenland, Chief Sustainability Officer at Dassault Systèmes, to tell us more about designing disruption, the critical role of virtual twins in accelerating sustainability.
Okay, great. Thank you. I just want to check if you all can see the screen, because it went gray for a second. Can everybody see that? I was told that they could see it and then they couldn't.
I confirm that we can see it.
You can see. Okay, great. All right. So I'm so happy to be here. Thank you very much for the invitation. I wanted to talk to you a little bit from the corporate perspective. I work for a company that makes virtual twins of anything, really, and talk to you a little bit about how we are working on climate action from this particular technology and this particular perspective. So Dassault Systèmes is a company that provides business and people with 3D experience universes, so virtual universes, to imagine sustainable innovations capable of harmonizing product, nature, and life. In a nutshell, this is sort of who we are. So world leader in 3D design and engineering software. It's a company with about 200,000 employees, about 300,000 customers, often seen as a very innovative company because virtual twins are still quite on the cutting edge of technology today, and even more on the cutting edge if you think about their use for sustainability. And then on the right, you see a little bit of some of the recognition in terms of environmental, social, and governance issues. And we are very proud, notably, to be a founding member of the European Green Digital Coalition, which is why we're very happy to work with the EU on a lot of this. So this is an overview just of our sustainability strategy. We have a series of targets for 2025 where we focus on our own footprint, also on the products and services we deliver to customers and the world, and those include many governments today, in fact, and how we work with stakeholders. So in particular, you'll see with respect to our product portfolio, we have a goal to have 2/3 of new licenses from sustainability impact software, and lifecycle analysis is in fact a core part of that approach. So I'm going to jump into that a little bit more later. So I don't think I need to get into a lot of this because you all know this, but this is the United Nations decade to deliver between 2020 and 2030 because we have really hit crisis mode, both in terms of climate, biodiversity, ecosystems, land use, sea, everything is being overexploited, and we are hitting up against those planetary limits in some ways faster than we thought. We would. And so this is what we call the decade to deliver, because now we really need to change the way we manufacture and consume and do just about anything, as we will get into later. So there are now less than 10 years to achieve that goal. And essentially our belief is that incremental change is no longer an option, and we have to move to much more disruptive models, which is part of why virtual twins are helpful. So if you look at how virtual twins are being used today, they're very much being used for a couple of different things, but one is for very disruptive innovation. So 85% of the world's electric vehicles today were made using this type of software, 75% of the world's wind power. So anything that is a really disruptive technological change, essentially people are building it and simulating its use in virtual universes before they release it. And that allows you to accelerate the time to market and get these innovations out there in a record time compared to what you would have to do if you actually had to build physical prototypes, test them over and over again, see if they worked. You were talking about decades of work. So we can reduce that decades of work into several years of work thanks to virtual modeling. And this is an example of another way they're being used, which is connecting to IoT technologies, sensor technologies, the Internet of Things, to be able to provide constant feedback loops. So if you look across all the major categories of emissions, virtual twins are being used to first model the system, then collect data thanks to the sensor and real-time data, and then adjust that system. So figure out how to do predictive maintenance, figure out how to adjust things. This is used very often for energy efficiency in buildings, for example. You can monitor a whole building parks and simulate them, but also any kind of other industry as well. And this is just to get a little bit more precise in how they're being used. So at the very, very upstream, the virtual twin can help in the research and development process by doing in silico development of new materials. You can get to the molecular level and design completely new materials that didn't exist before. So we're doing a lot of work on biomaterials, obviously, and more sustainable materials. You can do the life cycle impact of those materials, then design and engineering. So same thing, you can do in silico design, you can do generative design, and so on through up to logistics. If you're modeling your logistics system, you can also optimize it, for example, for CO2 reduction. You can model sort of things like reverse logistics, which are how you would be able to get back the product that you've put back out on the market. So how can you bring things back and reuse and recycle them or refill them in the case of consumer goods. Product asset use is a little bit what I've just talked about. So you can monitor the actual operations and use of a system or an infrastructure, and then decommissioning and end of life. So you can, that actually has to do with the designs. You can eco-design something for end of life, including its dismantling, but you can also simulate that dismantling and track each material through the system. So we strongly believe that virtual universes are going to be a key tool for our customers, but actually for the world, to radically innovate new products, materials, and processes for tomorrow's sustainable economy, and do that at the fastest possible speed. So that's a little bit what I was talking about before, but this sort of idea that you need to disrupt, and disruption is very hard. You think about a large corporation that's manufacturing something, it takes multiple years just to adjust certain production lines to produce different things in a different way. So imagine trying to rethink everything, your materials, the way you're producing. How do you get to zero carbon manufacturing? How do you get plastic out of your products? How do you move to a circular economy model where you're not just selling product, you're taking it back and reusing it? So these types of changes are really profoundly disruptive, and virtual universes is a way essentially to practice and to play and to invent. And one of the best examples is from one of our customers who was involved in building one of the first electric glass manufacturing plants in the world, which nobody thought was possible 5 years ago. And the only way to get the capital and the partners to do that project was to prove that it was possible in a virtual universe first. So to simulate that you could get to the right levels of heat, the right levels of fluidity, you could make a manufacturing plant run on renewable energy at that speed and at that level of energy intensity. So these types of breakthrough products and breakthrough inventions that we need right now are already today being built with this technology. And so we did a little bit of work with Accenture to try to quantify the impact. Again, this is a very cutting edge technology. It tends to be used by at large scale folks who are already quite digitalized and are using rather sophisticated either production systems or very complex products, building very complex products. We also have another part of the business which is very accessible and is more about 3D modeling. But some of the examples I've given are more on the complex side. So we know that there's space for this to be used by more people in more contexts. And if we are talking about the sustainability revolution here, we think this is a tool for everybody to have, essentially. So we looked into 5 different use cases and said, well, if you took these from being just use cases to essentially being very common across those industries, what would the impact be? In terms of economic value and CO2. So we got to a conclusion that you could essentially save 1.2 trillion in economic value. That has a lot to do with not having to try and fail for years and years and years, but actually getting it right the first time and getting new ideas out there faster. And same on the CO2 side, 7.5 gigatons, which is the equivalent of today's transportation sector. So very significant impact. And I can just walk through what those 5 use cases were. Cities and construction. So this had a lot to do with reducing energy consumption in buildings in the operations phase. Consumer packaged goods. This was about eco-design. So about 80% of the impact of a product is predetermined at the design phase. And what's happening right now is we're essentially doing product footprint measurement after it's on the market instead of in the design phase. So that's what this allows you to do. Transportation and mobility. So this is about accelerating the time to market for new mobility systems, especially electric vehicles. Life sciences. So if you look at pharmaceutical manufacturing, for example, the impacts on waste, pollution, resource consumption can be radically reduced if you're modeling those production plants and those production systems and running them with virtual twins. And then high tech. So for electronics, how do you embed circular economy principles, again, in the design phase to address the growing problem of e-waste globally? So these are direct impacts where you can essentially imagine different ways of building things, different ways of doing things in a virtual universe and dramatically reduce the real life impact. So this is my last slide, driving systemic progress with virtual twins. So this is just to show, sort of summarize what we see customers using these technologies for today. So we see a lot of our largest customers really trying to get serious about sustainability, about climate action, including how the SDGs can be embedded into their product manufacturing and innovation processes. So rethinking how the product lives from cradle to grave, or even from cradle to cradle now, with a circular approach. Also, we know that they're using these technologies because they can make the transformation simpler, faster, and cheaper. And then lastly, because there's a very high degree of predictability. So these are models that are actually more about science than they are about tech. So about material science or about fluid mechanics or about thermodynamics. So the science that's built into the simulation capabilities, also the engineering capabilities, but the simulation capabilities essentially are allowing people to innovate and be very sure of where they're going with those innovations. So if you want it to reduce CO2, you can model that and you can simulate that and make sure that it will do what you think it's going to do. So that is a zoom on this particular technology, how it connects with the climate agenda. And I am happy to answer any questions if there are any. And otherwise, I will give you the time back because I see we were running over a little bit.
Many thanks for the very interesting presentation. We have a question particularly addressed to you. There is a participant saying that that's very insightful. And what's the biggest challenge in achieving sustainable manufacturing from your point of view, and how to tackle that?
Oh my goodness. Yes. Sort of sustainable manufacturing. I think there's two issues when you talk about this. One is, energy sources, right? So greening the energy sources themselves that are behind manufacturing systems. So that's one thing, and that's something I think everybody is very focused on, and governments are very focused on greening their energy sources. So that's one element. And then the other element actually has to do with the circular economy and how we are manufacturing things and for what purpose and what use. And I'd say that that piece is the piece that is the hardest to crack, because if you have to rethink all of your formulations, you have to rethink all of the materials you're using. You have to rethink how you will break down your product at the end, be it by biodegrading or recycling or sort of recuperation and reuse. Those are pretty fundamental changes that really change the way you manufacture things, and could mean that a plant that works fine today will not work fine tomorrow. So a lot of this, there's a lot of connection between this technology and things like 3D printing or modular, adaptable type processing plants that allow for more flexibility in manufacturing than what we traditionally have had. But there's a real issue with scale. So I'd say the main issue, the main challenge, I wanted to give just one answer, would be getting it to scale. So there's a lot of today pilots being run, experimentation, new products, new ways of building them, new ways of thinking. Very few of those have the capacity to be scaled up to the level of, like what a Unilever produces every day or what a P&G produces every day. It's very hard to get an idea into an industrial process.
Thank you so much for answering this question. Moving to the next one. What SDGs are considered the most challenging by your organization in terms of digital twins?
So first of all, it's a great question because it allows me to touch on something that's quite surprising for most folks, which is that actually virtual twins can be used for modeling, like we've seen here, industrial equipment or cars or buildings or bridges. They can also be used to model like the human heart and human body and health systems and things like that. So for example, virtual twins and virtual clinical trials were being used essentially for most of the COVID vaccine clinical trials over the past few years. So most of this is being done virtually now. So there's actually a very wide range of uses for this. So you can focus on some of the SDGs related to health. If you think of it in that light, the examples I've given here are very much focused on sort of climate, getting to that net zero manufacturing, or getting sort of plastics and petroleum out of product design, things like that are a big part of our focus, just given the nature of the technology.
Thank you so much for your reply to that. I'll just open the floor for more questions to all the panelists in the remaining time that we still have. And we got here a comment from a participant saying that building exascale machines, particularly in Europe, would also have an environmental impact. So maybe if one of you would like to comment on this, particularly on the other side of the angle. So would maybe you, Mr. Anders Jensen, would like to start?
Sure. I mean, that's correct. Of course, there's an environmental impact for any production. I think the interesting thing is that we have a certain reputation within Europe to take that very seriously. So hopefully, through the use of European technology, we will be able to have a significant impact on that and introduce technologies that will be more environmentally friendly, energy friendly, etc. The fact is, we need the machines. We need to be able to do these things in order to help the environment largely. So it is, of course, a paradox that the calculations themselves do consume energy, but it is really to solve the bigger issues, and hopefully, therefore, the net effect is hopefully that we will have a positive contribution to the environment.
Thank you so much for this. If any of move then to the next question. So there is another question related to, I note the World Climate Research Program Strategic Plan 2019-2028 is highlighted. Can you attempt and envision the post-2028 strategic plan, example, the best case scenario? Maybe this question.
Yeah, so it's a difficult question when you look. You can look back what was there 20 years ago and where we are now, and there was things that were already there 20 years ago when we're just tackling now. So it's always very difficult. No, I really believe that one of the big changes we will have is in the way we will envision what we call now impact studies. It will be something more integrated. We will be able to look across. When you think about the SDG sustainable goals, they are all interlinked, and we still have everywhere a thinking that is only for one sector of activity or so on, and then we will be able to look at these interconnections so in the broader thinking. At the moment, is too much disconnected somehow. So that will be the big change, I think, for the next strategic plan. And of course, there will be, but maybe this is for Peter. There will be more possibilities in prediction for some of the timescales, and we will have a better way to integrate what's going on smaller timescales, what's going on long timescales. There's also a big deal, and it's connected with risk, and it's connected with extremes. Is that there's a big questions now going on the way climate change will affect these extremes, or these extremes play a role in the climate. And this also requires quite a lot of investigations, and there are lots of different types of extremes. And this will be also something where we will have lots of progress, I think, coming in, and new ways of looking at them and be able to interact with the different sectors of activities or the decision making. So that's that's part of it, and of course more better knowledge, better integration with society for what is human activity, and not only the one we are looking at now in the system. So I don't know if it answers, so that would be the best case. But it's possible also that we are still trying to understand, as it is today, some very fundamental aspects in the system, and that these new aspects will be revealed by some of these extreme simulations that will come in the future thanks to the increased computing facilities to do it.
Thank you so much for your intervention. Is there any other speaker who would like to intervene on this?
I could probably add to what the question on the World Climate Research Program. You can kind of smell where the next strategy is going through what the World Climate Research Program is calling lighthouse activities, in which Pascal is also participating, which indicate, like flagship projects that particularly concerned with climate. And that try to focus actions where better information is coming from, and what we need to know, actually. And I think some of this Pascal has mentioned already, but some of the big themes there are to be better at attribution, so that we really understand what changes that we can see in terms of extremes or mean shifts are actually related to human-induced climate change, and which aren't, which others are part of the natural variability background that needs better prediction systems. Another important one is what's called safe landing places, which has to do with, accepting climate change to a certain degree. Which scenarios for change actually will be acceptable for the bulk of mankind in one way or another, and which aren't. It's a very nonlinear system with many degrees of freedom, and there are tipping points in certain areas related to, where the environment is just going to drastically change, and the change is irreversible. For example, if ice sheets melt entirely, for example, that's not something that you're going to rebuild even with the most drastic greenhouse gas emission reductions in the next 100 years or so. So we need to understand where those lie, and how we can derive political action to land in these safe places. And the third is actually called Digital Earth. And that's about what we were trying to cover in Destination Earth to a certain degree, but scale that up, of course, to the globe, where we say, you need digital twin-like platforms at that scale, as we're trying to instigate with Destination Earth. But that needs to be a much bigger, much broader, much more convenient platform to use for everybody, for science and society. And how to link this, for example, to the more industrial, very specialized digital twins that Alice has mentioned. Ideally, you couple digital twins laterally, the one on food production with the one on water resource management and the one on car production, but also vertically with what we're trying to do at global scale related to environmental change and climate.
Many thanks for your intervention. Would any of the speakers like to add something? If not, we will move to the next question, and we have a participant asking about the European clouds that currently exist, and if Europe is moving towards HPC cloud to address and compete in solving the complex problems. If it's there anyone who would like to pick this one related to cloud.
Well, I can definitely say it is on the to-do list for the new regulation to make HPC services available in a cloud fashion. We still need to exactly figure out which initiatives we'll link into and how we'll get this done. it's on, as I said, it's part of the work that's foreseen under the new regulation. So stay tuned, and we'll hopefully get wiser.
Thank you so much for your reply. Would any of the other speakers would like to intervene on this? Okay. Otherwise, I would like to repeat to you, because we are receiving many questions related to the presentations and the videos. Indeed, so all these materials, there will be for review afterwards. They will be published on YouTube and also on our Connect University webpage. Most probably as of next week, but we will keep you posted on this information, so you will be able to review all this on our website very soon. So no worries, all the materials will be available for you very soon. So as we are approaching 4 o'clock, I would like to thank all the speakers for their very interesting presentations, and also to the participants. Thank you so much for the great feedback that you're providing us. Thank you for joining us in such high numbers. And just to remind you that tomorrow, as of 10 o'clock, we look forward to welcoming you to the event on energy consumption of data centers. And then we will have the opportunity to discuss more about the environmental impact that we all have when, for instance, we do a search on the internet or simply watch a video. So we look forward to welcoming all of you tomorrow at 10 o'clock. And also don't forget that registering and attending more than 7 events will bring you a Connect University diploma. Thanks again to all of you, and see you in the next sessions.
Thank you very much.